Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Alex Gu from MIT, who will tell us about LeanDojo, a system for developing theorem provers in Lean, and their work Reprover, Lean-Infer, that uses language models and generates proofs in Lean. So should be a very interesting talk. Yeah, you should probably mute briefly. As I always do, I offer to watch the chat. So if you have a question that may have a simple answer, you can put it there and I'll let you know or ask the question or encourage you to ask the question. Alex is happy to have questions during the talk, and there will be several minutes at the end for questions. So with all that, please, Alex, again.
Okay, yeah. Thank you, Mike, for yeah. Thanks, Mike, for the should I hello? Hello, test. Good. Okay, cool. Yeah. So thanks, Mike, for the introduction, and I'm very happy to be here today. I'm Alex, and today I'm excited to talk about our recent work on LeanDojo, theorem proving with retrieval-augmented language models. And this work wouldn't have been possible without my great team of collaborators, Caillou, Aiden, Raul, Peiyang, Shixing, Saad, Ryan, and Anima. So automated theorem proving has been a longstanding challenge in both the programming languages and machine learning communities. And in theorem proving, we're given a set of assumptions and a desired conclusion to prove. In this case, we assume that n is a natural number, and we want to derive the closed form formula for the sum of the first n natural numbers. So we consider a setting where both the assumptions and the conclusion are expressed in a formal logic, for example, first-order logic. The goal of the automated theorem prover is then to come up with a formal proof of the conclusion from the assumptions. There are many applications of formal proving, such as in verified software, hardware, or formal mathematics. And these are all applications where you don't want errors. Say you don't want bugs in your code, you don't want hardware failures, you don't want a supposed proof with an error in it. And so therefore, in these cases, you want to formally prove 100% both correctness and security. You can imagine how difficult it would be to keep track of everything when writing down a formal proof for a big system like this. So fortunately, there's these things called proof assistants to help humans with the process of writing proofs. And some common examples of proof assistants include... Oh, I didn't screen share. Sorry. Do you want me to go over again?
Well, I don't know if you can repeat everything.
Okay, yeah, I can flash the slides. Yeah, so here you have a set of assumptions, and the goal is to derive some conclusion. You have the automated theorem prover that helps with this. And in this slide, here are just some applications of theorem proving. Right, yeah, so there are things called proof assistants that help humans with the process of writing proofs. And some examples of these proof assistants are Coq, Isabelle, and Lean. And so now I'm actually going to switch to a demo where I show off what a Lean proof assistant might look like. So let me switch. Okay, so can Zoom see the screen here?
No, I think you have to share each separate.
Okay, cool. So in this window, what I'm showing is a demo of using Lean in VS Code. So this is an extension called Lean Prover. So what I've done here is first in these lines, I've defined a factorial function. So factorial of n is going to be, the standard factorial function, right? So it takes in a natural number as input and it outputs a natural number. And so what does a factorial function do, right? If the natural number is 0 factorial, we define is equal to 1. And if we have the factorial of a number n plus 1, it's going to be equal to n plus 1 times the factorial of n. So a very recursive factorial definition. And I'm going to show you how to prove a theorem called fact-pos. It's a very simple theorem. If n is a natural number, then 0 is less than the factorial of n. So let's step through the proof to see how proof editors and IDEs work. So here on the right, what I'm seeing is actually the state of the proof, right? So at each point, I can see the state of the proof. So right now, I haven't actually, so I'm stepping through the proof line by line. Let's say I'm here, I haven't actually proved anything. So what does this show me? N is a natural number, and I want to show that 0 is less than the factorial of n. So this is this turnstile, it's called a turnstile, and it gives you what you want to prove. So the first thing we're going to do is we're going to run this. This is called a tactic. So what we're saying here is that we want to run induction on n, right? And IH is going to be the name of the inductive hypothesis. So there's two cases for the induction, right? Either n is equal to 0 or n is equal to k plus 1 for some k. So let's step into the first case here, right? This dot means we're stepping into the first case. In the first case, it shows us exactly what we want to prove. This is one of the nice things about theorem provers. And so it says we want to prove that 0 is less than the factorial of nat dot 0. Right, so this is pretty straightforward. And what we want to do is we're going to rewrite with the definition of factorial. After we rewrite with the definition of factorial, factorial says that 0 factorial is equal to 1, right? And so the goal becomes 0 is less than 1. And this is very easily proved with a tactic called simp, which simplifies 0 is less than 1. And it says it's true. Now let's go to the second case here, right? So we proved the first case. Now we want to prove the second case. In the second case, now you can see that there's an additional inductive hypothesis here, right? So we know that 0 is less than the factorial of n. This is exactly what you'd expect if you're doing a proof by induction. And you want to prove that 0 is less than the factorial of the successor of n, which is n plus 1. The proof is very similar. In this case, once again, you can rewrite with the factorial, which now you see it's using the other case of the definition, right? 0 is less than n plus 1 times the factorial of n. And it turns out that simp is relatively powerful. It actually says, okay, well, let's simplify. Let's rewrite this into 0 is less than factorial of n. So if you can prove 0 is less than factorial of n, then we're done. And so the way you prove this is, well, we already have this inductive hypothesis that says exactly what we want. And so we use this tactic that's called apply. And what apply does is it says, if you have a hypothesis, then the conclusion is true. And so now we have no goals, which means that this theorem is proved. Any questions on this?
Can you say a bit more? What is rewrite?
Yeah, so rewrite essentially means that you're taking the definition of factorial and you're rewriting it in the thing you want to prove to simplify the expression. So for example, before this rewrite, we wanted to prove that 0 is less than factorial of nat dot 0, right? And the rewrite takes fac of nat dot 0 and it says, oh, actually by definition, because here we have factorial of 0 is equal to 1, we rewrite 0 is less than factorial of nat dot 0 into 0 is less than 1, because we know that factorial of nat dot 0 is equal to 1 by definition.
Cool.
Yeah. Okay, so this is the demo. Let me go back to the slides here. Is it shared on Zoom? No, it's not. Okay, awesome. Cool. So now that you have a sense of how Lean can help you prove theorems, right? Now let's walk through a slightly more complex proof. Here we're going to prove a theorem that's called GCD self. Assuming that n is a natural number, the GCD of n and n is equal to n, for something that's relatively simple. So on the right, what you see is a proof tree, which lists the proof states we've seen so far. The proof tree starts with just the hypothesis and the goal that's given in the theorem. The first tactic that we use is called cases n. In Lean, a natural number is defined as either 0 or the successor of another natural number k. So therefore, cases n splits the proof up into two cases based on whether n is equal to 0 or n is equal to k plus 1. So in the first case, we use this tactic called unfold, pretty similar to rewrite, which replaces GCD by its definition, which says that the GCD of a number is 0 and y is equal to y. Moving on to the second case, we again can apply unfold GCD. We get this new expression by the definition of GCD when neither term is equal to 0. So I won't go into the specific details here, but you can think of it as reducing the GCD of x and y to the GCD of y mod x and x, kind of like one step of the Euclidean algorithm. Next, we'll use a theorem called mod self, which says that any number mod itself is equal to 0. You can see how the proof state transforms here. And finally, to conclude the proof, we apply a theorem that's called GCD 0 left, which says that the GCD of 0 and any natural number is itself. This concludes the proof. So as you can imagine, the bottleneck in this process is for humans to come up with the right tactics, like mod self, GCD 0 left, etc. The human has to be pretty familiar with both the underlying mathematics and also the proof assistant that they're using. And even so, finding the right tactics requires a lot of trial and error. This is especially challenging if the tactic relies on a premise, that is, a lemma, from a very large library of existing math. So that's exactly where machine learning can help. We aim to automate this interaction using machine learning to generate tactics. And we highly believe that this promising approach is very complementary to existing proof automation techniques that are developed by the formal methods community. We'll focus on a class of models widely successful in machine learning, large language models, which we'll abbreviate as LLMs. They've shown impressive capabilities in both math and coding. For example, GPT-4 proclaimed to score in the 89th percentile in SAT math among human test takers. We've also seen LLMs have enabled practical coding tools such as GitHub Copilot. Since theorem proving requires both mathematical reasoning and formal proofwriting, which is very similar to code, these language models are a very natural choice for the task. So let me motivate this a bit more. First, we need advanced mathematical reasoning at some point in our future. And maybe it's not going to be sufficient to just train bigger and bigger models. Perhaps something like rigorous or formal representations will play a significant role moving forward. In addition, language models are quite hard to evaluate, and they tend to hallucinate with invalid reasoning steps using methods like chain of thought. In natural language, these things can be pretty hard to check. But since formal proofs can actually be checked very easily, they provide a very rigorous evaluation with almost no room for hallucination. And it's not just me that believes in large language models and theorem proving. We've actually seen quite a few works in this area already in the last few years in various languages like Isabelle, MetaMath, Lean, and also Coq. At a very high level, these methods take in a proof state as input, sometimes with other auxiliary information like the theorem name. And generally, they output a tactic to be used. But sometimes the output can also be the full proof, whether to use other automation tools or other useful information. Despite all these awesome existing works, the area is actually facing a pretty significant barrier because none of these existing methods can be reproduced by a reasonable amount of effort. So let me elaborate a bit on that point. Here are a bunch of works on language models and theorem proving. First, many of them rely on private datasets. Here, a checkmark means that the dataset's publicly available, X means unavailable, and the orange hybrid means that only part of the data is actually available. For example, Baldur in the third row here uses public datasets for fine-tuning, but uses Google's Minerva as their pre-trained language model. And so the pre-trained data here is completely unavailable. Second, none of these have released either model checkpoints or code bases for both training and evaluating the model. Third, theorem proving requires a tool for the model to interact with the proof assistant, but only some works have released this interaction tool. And finally, the compute requirement in prior works ranges from 1K GPU hours to 48K GPU hours. And this is quite exclusive to industry labs with extensive resources. So it's a bit unfortunate, in my opinion, that although the area has been around for a few years, there's surprisingly very little for newcomers to build on. And we believe that this is a huge barrier to research in LLMs for theorem proving. In this work, we introduced LeanDojo to address all these aspects. LeanDojo provides datasets, models, code, and also an interaction tool, all of which are completely open sourced. Our model is relatively inexpensive and needs only 120 hours to train on a single GPU, which provides researchers access to state-of-the-art large language model-based theorem proving with modest computational costs. So now that all of you are now interested in LeanDojo, I'll dive into the details of our tool. Our tool is designed to work with the Lean proof assistant, both Lean 3 and Lean 4. Next, let's see the overall pipeline of LeanDojo. First, we need to extract a dataset from a set of Lean files. In our case, it's going to be a large library of math theorems, which is called mathlib. We use this dataset to train a model from scratch. In our case, we do byte-T5 with 299 million parameters. Once trained, this model can then prove theorems by interacting with Lean programmatically. And LeanDojo provides this entire pipeline. Let's start by talking about data extraction. So what kind of data would you want to extract? Most machine learning models take a current proof state and output the next tactic, as we saw before. So we want pairs of states and tactics. When we find Lean files on GitHub, we get code that looks something like this. we can first parse it into AST to extract the different tactics. This is relatively easy, but extracting the proof states is more involved since they're not directly available in the source code. And so we'll have to reconstruct the full proof tree by running tactics line by line. This gives us the proof state before and after applying each tactic, which is important when we're training our model. In LeanDojo, we extract these states using metaprogramming in Lean. Tactics also rely on premises, such as previously defined lemmas or definitions. These can be defined either in the same file or imported from other files. For example, on the right is a Lean file with the example that we saw before. The proof relies on premises GCD and GCD0 left, highlighted in blue and green respectively. These two are defined earlier in the same file. On the other hand, the premise mod self, highlighted in orange, is defined in another file that's imported into the current file. In LeanDojo, we do premise extraction so that we know exactly when each premise is defined and when it's used. This information will be useful when we train our retrieval model for premise selection, which I'll talk about later. So here's a very high-level view of how to extract data using LeanDojo. Given any Lean repo that's publicly accessible on GitHub, the repo has multiple files, each of which has a bunch of theorems. LeanDojo produces a data structure that's called a trace repo, which consists of trace files, and these have trace theorems. These data structures capture information such as file dependencies, ASTs, proof states, tactics, and premises. Users can then construct their own benchmark datasets by some post-processing. At a high level, we started with a Lean repo, which can be specified with a GitHub URL. LeanDojo then goes through the repo, extracting all the information about the repo into the trace structures that we just saw. These trace structures can provide plenty of information. For example, a trace file shows the dependencies, premises, and trace theorems in the file, and a trace theorem shows the location of the theorem in the file, tactics used in the theorem's proof, the proof state before, after, and so on. So now I'll show you a demo of how to do data extraction in LeanDojo. Yeah. Is it sharing? Cool. So yeah, now I'm going to demonstrate how to do data extraction in LeanDojo. So first, we just import LeanDojo, something like this, very simple. And what we see here is a lean git repo object, which is loaded from a GitHub library. So in this case, you see this is mathlib4, and this is the commit hash that we're loading the repo from. What you can do is also get the configuration of the Lean toolchain here. So when you do this, it shows you that, okay, well, we're using Lean4 and we're using this version of Lean4. There's a function called trace in LeanDojo. This is the meat of the data extraction step. This takes a while, so I'm not going to run it, but essentially it turns this repo into a trace version of the repo with trace files, trace theorems, and so on. So now once you have the trace theorems, what you can do is actually look at the graph of file dependencies, right? So in this case, when you have a trace repo, you can get the trace files graph. And what this graph shows, it's a list of edges showing the dependencies between different files in the repo. And so what are we going to do here? Right, so let's look at this link here. This is actually the GitHub. Oh dear. Yeah, so this is the GitHub file, something in mathlib, right? Quotient.lean. And we see that quotient.lean imports from all these libraries. And so we actually are able to extract these libraries in our demo, where we say, if we iterate through the graph edges, and the first node is going to be this quotient.lean, we're going to print out the dependency. And as you can see, it shows all the dependencies that this file depends on. So this is helpful for retrieval, as we'll see later. You can also see the number of traced files, in this case, 4264. And let's just get one of these trace files, right? So let's get this file, mathlib linear algebra basic.lean. And so the trace file is an object like this. From a trace file, what you can do is get the premise definitions. And I'm just showing one of these premise definitions. You see that there's the name, you see that there's code, shows when the premise starts, when the premise ends. So these are line numbers, and it also shows the kind of the premise definition. You can also check out the trace theorems. And let's actually look at one of these trace theorems here, right? So THM there's going to be this trace theorem that's called pi EQ sum unit. And so this is a trace theorem object. What can you do with a trace theorem object? First, you can show the theorem, right? So when you show the theorem, it gives you a URL and it shows you exactly where the theorem is defined, right? So this is the theorem that we were trying to get. When you can also, there's a theorem object, there's a start and an end. This shows you the lines. So in this case, we're seeing it's from line 151.1. And as you can see, it starts on line 151, ends at line 154, right? So all this information is given to you. It also shows you when this theorem was created, whether it has a tactic proof, and the number of tactics in its proof. So now let's look at the proof, right? So as you see in this lean file, the proof consists of two tactics, ext, extensionality, and simplify. We can also get this exact proof here. First, we get the proof node, and then we look at the full proof. You print the proof, and this is exactly what you get, right? You get these two tactics. We also have these tactics traced, as I talked about before. So trace tactics, when you run get trace tactics, it will give you these both, not only the tactics, it'll also give you the proof state before and after each tactic, as I talked about. So this might look a little bit intimidating, but what we're trying to show is, let's look at this first trace tactic, right? The simp. So simp has a proof state before and a proof state after. So the reason that you see state before might look pretty complicated is that it's not just looking at the variables that are defined here, but in this file earlier, there's also some other variables that are defined as global variables. And you see that our tool is actually capturing all of these global variables when we're getting the proof state, right? So you see R, S, K, M, and N, and these all show up like R, S, K, M, N, etc. But the thing to note here is that we see both the state before and also the state after, right? So by seeing both the state before, the state after is actually no goals, right? Because after you run simp, what happens? The proof is over, right? Remember, the proof was only 2 lines, ext and simp. And so in our data extraction step for each tactic, we make sure that we're able to get both the state before and the state after so that we can train our models. So that's the end of the demo for data extraction. And now let me go back to the slides. Okay, is it shared? Cool. So next, let's talk about our benchmark from Lean's MathLib, which is called the LeanDojo benchmark. We actually have 2 versions of our benchmark, one in Lean 3 and one in Lean 4. And in addition, it's very easy to construct your own benchmarks on repositories that are not MathLib, right? So we do the same data extraction process as we just saw. We actually provide 2 splits for our benchmark. In the random split, we can randomly select 2,000 theorems each for validation and testing, and we leave the rest for training. However, the issue with this split is that it leads to accidental contamination. So for example, here are 3 consecutive theorems in the same file in Lean. They look very similar, and actually the last 2 theorems have identical proofs. So this makes it very easy for the model to just memorize training proofs and split them out when they see similar test proofs, right? For example, if the first one were in training and the last one were in testing. To combat this, we add a challenging data split that's called novel premises, where each proof in the test set must use at least one premise that's never seen in training proofs. Now it's time to introduce our model for retrieval-augmented theorem proving. Let's go back to this high-level diagram of existing tactic generators. Remember that they take a proof state as input and output a tactic. One shortcoming of these methods is that actually at testing time, the model has no knowledge of what premises are available for tactic construction. And so this might make outputting the right tactic relatively difficult, especially in our novel premises split, where it has to use premises that were not used during training. Specifically, it can use premises only by memorizing their names during training, which might be inefficient or hard to generalize. We introduce our model called Retrieval-Augmented Prover, or a reprover, to mitigate this issue. Let's see how reprover predicts the next tactic from a proof state. At a high level, it first retrieves similar premises, and then augments the proof state with these premises to predict the next tactic. In a little more detail, let's say we first have the proof state in a file. And from that proof state, we look at all the premises that are accessible from that file and its imports. In this case, there's 33K. We then pass the state in the premises through an encoder, and we use the cosine similarity to find the most relevant premises. This gives us the top K retrieved premises, something like this. Here we use an encoder that matches proof states with premises. This encoder is actually trained with contrastive learning. So concretely, remember that in our LeanDojo benchmark, we have a data set of proof states alongside the premises that are used to advance the proof to the next proof state. We call these positive premises, and we train our encoder to minimize the distance between the encodings of the proof state and the encoding of the positive premises. At the same time, for each proof state, we also include a set of other premises called negatives, which are other premises that are relevant for the given proof state. During training, we want to minimize the distance between their encoding and the proof state's encoding. An important idea in contrastive learning is the idea of choosing hard negatives during training, or negatives that may look like positives. This way, the encoder can learn to distinguish true positive premises from premises that look similar but are actually unrelated. In Reprover's encoder, we choose these negatives to be random premises in the same file as the positive premise, which is called in-file negatives. We saw that this improves performance when compared to just choosing random premises from the entire set of all premises as negatives. After the retrieval set, yeah.
I mentioned this in our conversation, but I'll mention it again anyways. So you're comparing, you're basically looking at similarity between embedding of premise and embedding of state, which are similar. They're written in the same language, but of course they are kind of different things.
Yeah.
And did you consider either putting in like some sort of transformation that it could also learn that would pick out like piece of state, which should look like piece of premise, or as a divisional DPR, even two encoders?
Yeah, so right now we're only using one encoder for both the proof state and the premises, but I do think that it's very possible that using two encoders, separate encoders for the proof state and the premises may help the performance. Any other questions about the retrieval part?
Just to clarify, you train from scratch?
Cool. So after the retrieval set, we have a set of retrieved premises that are relevant to the proof state. Next, we augment the original state with these retrieved premises until they exceed the context length, which in our case is 1024. We pass the concatenated proof state and premises into a byte T5, which predicts the next tactic. We see that Reprover is actually effective and that retrieval helps. Here, the green and red bars show Reprover with and without retrieval. As baselines, we use Tidy, which is Lean's built-in automation tactic, and GPT-4, both of which underperform Reprover. Especially for our novel premises split, we see modest boosts from both Reprover and retrieval. We also see some success on MiniF2F and ProofNet, which are two benchmarks for university and undergraduate level mathematics. These benchmarks actually have many theorems that remain unproved and for which ground truth solutions don't exist. So as a fun side note, we were actually able to discover a couple of new proofs here. Many of them are actually relatively non-trivial. You can take a look. Finally, we also provide a nice API for interacting with Lean. Our API provides an interface for machine learning models to observe proof states and run tactics. It actually has two functions. So the first function is initialize, which takes in a theorem and returns the initial state. The second function is run tac. It takes in a state and a tactic, and it does exactly what you think it does. It takes the state, runs the tactic, and returns the next state. So these two API functions are very useful when we want to interact with Lean. So let's say we're in the search process. We start with some initialization for a theorem. We want to run some tactics, and we want to see what happens. I'll show a demo of this later. We find that our API actually has a much more reliable interaction with Lean 3. So the existing Lean gym actually misjudges 21% of correct proofs as incorrect, whereas the error rate's only 1.4% for LeanDojo. We document these errors on our GitHub repo. Our LeanDojo is also the first tool to interact with Lean 4 programmatically. So now let's see a demo of how to interact with Lean. Okay.
You still need to share.
Oh, sorry. Yes. So as before, after this last section, we still have the same repo as we had earlier, right? So this is a LeanGet repo with mathlib4 and this commit hash. So this is the entry point to the interaction through tactics, and this is called Dojo. So what you do is you take a theorem. Let's say in our case, this is going to be mathlib basic.lean, and this is the same theorem that we saw earlier. So for some theorems, this might take a long time, so I've actually preloaded this already. And so in this case, you have this Dojo and you have this initial state. And we use this entry point, enter, to have like an initialization for the theorem, which I just talked about. So this is state 0, right? State 0 is actually the state before you enter the theorem. The state, let's say you just entered the theorem, and this is all the variables that you have. So let's see a pretty printed version here where you have, it's very similar to what we saw in the last state, but we see all these variables that were defined earlier in the file. And then we also have this x, right? This is the same x as in this theorem here, right? In this theorem, you have this x, and you want to prove that x is equal to, oh, yeah. Here, okay, yeah. So right, this is the x that we're looking at here, and we want to see that, well, this implies this. Yeah, the exact details of what this is saying are not necessarily important here. So as you notice, what we just saw there is also what we see here, right? So you have this x, you want to show that this, you have this equality, and then you want to show this implication. What we can do is from this state, we can actually start running tactics with our LeanDojo tool. So if one tactic that we might want to run is called revert. So what this revert does is actually, it says that in this state, you already have this x, and you want to show that x is equal to this implies this. When we run revert x, what we do is that we remove this x, and we say that for all x of this type, you have that this is true. So let's make sure this does what we want it to do. We have this new state 1. State 1 is what happens when you take state 0, you run revert. And as we see, this is exactly what we want, right? So after you run the revert, now you have this for all x, you have this thing that we saw before. So LeanDojo can also handle when you run tactics that aren't necessarily correct, right? So in state 2, let's say we run this unknown tactic that's called hello world, right? Clearly not a lean tactic. When we get to state 2, when you print out this state, it tells you that there's a lean error, right? So this is the error that you would expect, unknown tactic in lean. And whenever you have a lean error state and you try to run any other tactics, this will throw an error in Python, right? Because this is, you're starting from a state that's not actually valid. You have an error in lean already, and we don't want you to do anything else. So I can run this, and it will, yeah, it says attempting to run a tactic on an invalid state, lean error, which is the expected result. You can also run this sorry tactic. In lean, when you don't know how to finish a proof and you just want the proof to be over, you run sorry, right? And so it's kind of like a given up state. And so therefore, when we run sorry on any state, we basically get a proof given up, right? So here, dojo.run tac, state 0 is the initial state, and then we run sorry, and we have a given up proof. And then we also have this pretty printed state, once again, state 0. And now we're actually going to simulate the real proof, right? So recall before, the real proof has 2 steps, ext and simp. But what we're going to do is we're going to take this initial state, we're going to run these 2 tactics through, and we're going to see that LeanDojo shows us that we have a complete proof state. So first, let's run ext. It shows us exactly the state that we get after running ext. And then we run simp, right? So ext gives us a state 3, and then starting from state 3, we run simp. And as you can see, when we run state 3, we get this state 4, which is a proof finished state. And this is exactly what you'd expect. And finally, we have this is successful flag. When we say dojo.is successful, what that shows is that, well, you've run a lot of tactics and you've finally gotten to a proof finished state. So in LeanDojo, what we do is we kind of simulate all these running tactics in Lean so that either you or other people developing machine learning models can simulate Lean in Python. So that's the end of the demo. Now I'll go back to the slides. Okay, so with that, we've covered the entirety of LeanDojo: data extraction, benchmark, model, training, retrieval, and also interaction. So now I'll talk a little bit about some future work that we're interested in. So first, we want to integrate LeanDojo with GPT. And so I'm going to show this quick video of how you might be able to accomplish this. So we give it some instruction and we say that I want you to prove this theorem in Lean. And what it can do is it can make calls out to LeanDojo, right? And so, for example, you have this example. It's like a plus b plus c is equal to a plus c plus b, right? So that's the initial proof state. And it does some reasoning about what the proof state is. So you can read what it's trying to do right now. And so now GPT actually gives this high-level plan for proving the theorem. So it says you should use associativity and commutative properties, and it tells you how you should prove this theorem. So the interesting part here is that we allow GPT to actually use LeanDojo to execute tactics and get the next state back. So in this case, it's rewriting with add assoc, which is like associativity. And when it queries from LeanDojo, LeanDojo gives it the new state back. Now it says we're going to use this next tactic, rewrite add com BC. LeanDojo tells it what the next state is. And LeanDojo also says whether the proof is finished. So now GPT tells it, let's rewrite with one more tactic. And LeanDojo actually says, well, proof finish is actually true now, right? So you've ended the proof. And so GPT knows that we've ended the proof, and so it's not going to try any more tactics. And one cool thing you can do is you can ask GPT, well, now you've had all this interaction patterns. Can you show me the final proof that you found? And actually, it's relatively good if it's able to actually prove the theorem, right? It shows you the theorem, it shows you begin, it even annotates some of the steps, and it shows you the full proof. It even generates some text. So yeah, it took a bit of iteration. This is one of the cleaner examples, right? So if you try harder theorems, that is definitely one limitation of GPT, right? Because, as I showed in the results, GPT's performance isn't super good at more non-trivial theorems. And so this is like a very, very easy theorem, right? A plus B plus C is, A plus C plus B, right? This is the type of thing that GPT might actually know how to prove. But we have tried a lot of harder theorems, and it seems that GPT does struggle to find the right tactics just because it's also not really using LeanDojo's retriever as premise selection. So we do think that there's a lot of future work in integration, and GPT is especially good with natural language. And so we think that with LeanDojo integration and some more natural language, it's very possible that there's a lot of potential for using GPT to improve theorem proving. Sure. So one of the undergrad authors, Pei-Yang Song, is actually also working on using LeanDojo to build practical LLM-based proof automation tools. And this is trying to enable machine learning to help aid human users. And so in a sense, you can see that here you have a set, so this is like a VS Code IDE. And what's special here is that you have this suggest tactics thing right here. Suggest tactics. So when you type suggest tactics, this is like lean infer. And what we're doing is we're trying to infer tactics to apply. And this is using LeanDojo as a backend. And as you can see, this is kind of the pipeline. You take LLMs, you reduce it to Onyx representation, you look at some shared libraries, and then it kind of gives you, say, try this, try simp with these tactics. Maybe you apply this theorem, exact this, and so on. And so this is still work in progress. It's towards large language models as co-pilots for theorem proving in Lean. And that's kind of the goal of this part of the project. And that's it. Thanks for everyone here for coming. And once again, LeanDojo would not have been possible without an awesome team of collaborators led by Kai. So I encourage all of you to please feel free to try out LeanDojo. And if you have questions, concerns, feedback, we'd love to hear about your experience. Thanks again. And now I'm happy to take any questions.
Thanks, Alan. That was really great. We see a real glimpse of the future here. Questions?
Hi, I just want to clarify so that I really understand this clearly. So ByteT5 is a very
basically you trace all of those files using the library beginning, right? So like how can you say again how to use all of those trace information in the training? Like are they used as an input or is just like basically what do you put as the input of the
Right. So for the trace information, the key information that's missing from the Lean files is the proof state. And so if you go back to this diagram here, right, the model that we're trying to train, it takes as input a proof state, something that looks like this, and we want to output a tactic, right? And originally the Lean files don't actually have this proof state, right? The Lean files only have the lines and the tactics, right? So it looks something like this, right? The Lean files, they look like this. And so by tracing, we get, by reconstructing this proof tree, we get all these intermediate states. And so the input might be something like this, and the output would be unfold GCD. And so during training time, we concatenate like this. This is after this, and then this. And so what we're trying to do is, these are like the supervised inputs, and we know these are the supervised outputs. And
So
then,
the information, let's say like which line it is in.
oh, we're not using the information of which line it's in there. We are using that in the retriever, because when I talked about the in-file negatives here, right? In the in-file negatives, what we're interested in is we want to choose random premises that are in the same file as the positive premise as the negatives. And so that uses the information of which file is each premise in, right? Because if we just use random negatives, it's very likely that it's going to use negatives that are obviously different from the positives, right? So for example, actually, this is a pretty good example, right? So you have this proof state and it involves this mod. And the ground truth perfect proof state is like mod self and mod n is equal to 0. Right? If we just choose random negatives, you might get negatives that look like, the theorem that I was showing in the demo, which have almost nothing to do with this. And those are like obviously going to be negatives, right? And so the model doesn't actually learn anything if I tell it that's a negative, because the model probably already has a pretty far representation between that premise and this proof state. And so the point of having these in-file negatives is that now we're looking at the same file as mod self, right? So to choose negatives, we look at this mod self theorem, and then we say, look at the file that it's in, and then randomly pick other premises and lemmas, like mod 1 is in the same file as mod self, and so is this mod 2 eq 0 or 1. Right? And these look actually much more like this proof state, right? You could see that the model might, at initialization, might be confused between, well, should I use these two or should I use this one? And so during the contrastive learning training, we're using that information to push this one away from these two.
More questions?
Sammy has a.
So, yeah, one question I had, like, you talked about the model gets biased by some interaction between the tactics. For instance, I have tactics 1, like maybe 90% of the time after tactic 1, I use tactic 2. But maybe like 5% of the time I have tactic 1 and tactic 3. Does like the model fall into like learning these first correlations, or like are you able to escape them?
I think it's very likely that the model's learning these correlations, but in a sense, I also wouldn't say that it's a bad thing if the model's learning these correlations, because when we're actually doing proof search, we can look at all the possible tactics that are generated, right? So if it's tactic 1, tactic 2 often comes after tactic 1, then what you can do is like, okay, well, we try tactic 2, we see if we can continue the proof. If it doesn't work, we can then go backtrack and try tactic 3, right? And so in that sense, I think if it would be ideal, right, if you could learn in which context do you use tactic 2 versus tactic 3, but I do think that it's quite difficult to have all of that in mind.
So ideally, you would need like a backtracking procedure to be, like, for instance, I mean, this is normal, right? Like trap that you decide tactic 2, but maybe you can draw around, maybe
right. So in the search, we do that, right? We do best first search with some backtracking when we're doing the search stuff.
Okay.
Yeah. Yeah. Yes.
For actual training of the transformer, you're doing supervised training?
Supervised, yes.
Yeah, so it's closer to behavioral plumbing. Have you considered maybe doing like inverse reinforcement learning for the transformer model to see whether or not you could get additional?
Yeah, so I think that's reasonable. Oh, the question is vaguely, have we considered using inverse reinforcement learning to train the model instead of supervised learning? And the answer there is, right now we have a relatively big data set of supervised tactics, right? I think reinforcement learning would be pretty useful if you're trying to explore and come up with new tactics, right? Like new theorems, new proofs, all of that stuff. But for now, since we already have this supervised data set, we thought it would make a lot of sense to just do things in a supervised way. But we do think that there is definitely space for RL in the future for all this theorem proving and exploration work, especially when like coming up with proofs for theorems that don't actually have proofs. Yes.
So
What's the subject matter of the data set? One thing that I'm very interested in is applying proof tools to proving code.
The examples you showed were math.
Yes. Yeah, so we're mostly working in Lean, and a lot of the Lean libraries are for math. That being said, there are other languages like Coq, for example, COQ. Coq is a language where a lot of people have used that to verify software. And right now there's no tools like LeanDojo for Coq. I believe some people may be working on that. But for Lean, it's mostly mathematics, though the same types of techniques and methods should widely be applicable to other proof assistants for code as well.
Can I ask a
Questions?
question?
Yes.
So can you go to page 29? Oh.
Language models are good at translation. Did you consider trying to use language models themselves to translate existing rules in textbooks in plain language, right? Into Lean?
From plain
Part of
language,
it, we have not that many proofs in Lean, and we are aware of far more proofs than our code.
Yeah, I think that's definitely a valid concern. The data set size for Lean is actually not very large, though I do think that, so this is kind of very related to a line of work called auto-formalization. And so the goal of that is to take natural language and translate it to formal languages like Coq, Lean, MetaMath, etc. There's been a lot of work in that direction. Most of it so far has probably been like using GPT to directly zero-shot translate the natural language proofs to Lean. In our case, we believe that, so LeanDojo doesn't actually have any natural language, but we think it would be very nice if in some sense we had a paired annotated proofs in Lean code. So I do think that fine tuning should be able to help that if you get the data set of paired natural language in Lean. But right now everything's just zero shot in auto formalization. And so we didn't really look into how good that is, because you would have to have, like proofs are very brittle in the sense that every tactic has to be correct for it to go through. And so there's probably a lot of text out there, but I'm not sure what percentage of that text would be successfully auto formalized into working Lean code and proofs.
More questions? Well, let me ask, what's your group's plan for keeping this maintained, as a resource for the community, upgrading as Lean upgrades?
Yeah, right now, Caillou's been the main person maintaining all of this. We don't have a direct, plan for maintaining this as things get bigger, but we're also very open to contributions if people want to build off of LeanDojo. And if people are interested in helping maintain the tool, feel free to let us know.
Can you say a little more about who you are organizationally? Are you part of Lean?
Oh, I'm a PhD student at MIT.
Was the whole team in academia?
The whole team, part of it's in academia and part of it's at NVIDIA.
At where?
NVIDIA.
Okay. Yeah. Thanks. Have you had a response from Lean?
I think a lot of people who are working on Lean know of our tool, and Caillou should be more updated on that. But I think the Zulip chat is, people are talking about our tool there.
Can I ask more about the training part? Can you hear me? No?
Well, if not, let's thank Alex again for very impressive work and stimulating talk. And next week we'll have Yuan. We'll have a talk next week about, again, language models, UNG, I'm calling, and that'll be the same time. And so thanks for joining us, and we'll see you next week.